This is the exam review for Module 4, so be sure that you have your notes in front of you, that you've printed out the exam review. And this is on radicals. So the first section on radical expressions, in number 1, it's asking you for the opposite of, that's what that negative sign means, the negative root of square root of 121. Well, square root of 121 is 11, and the negative of that would be negative 11. Number 2 is asking you for the fifth root of negative 32. Notice that the negative here is under the radical sign. That's okay because our index is odd. So I can actually take the fifth root of 32, which is 2, and the fifth root of negative 32 is negative 2. Number 3 is asking for the fourth root of negative 256. Now this is different because this is an even root, and there are no even numbers that when multiplied times themselves will give you a negative 256. So we would have to say not real. In example 4, it's asking us for the third root of 64 over 27, which is the same thing as the third root of 64 over the third root of 27. The third root of 64 is 4, and the third root of 27 is 3. So our answer is 4/3. All right, and number 5, it's asking you to simplify the square root of 12 squared. Now you could definitely go ahead and square 12 and get 144 and then take the square root of 144. But what I'm trying to get you to see here is that squaring and taking the square root of something undo each other and just leave you with what is under that radicand. Same thing with number 6. The square root of x squared is just x. Here, the square root of x squared is x, but we want the negative of that, so that would be negative x. Notice the negative is on the outside, so it's just drug along. This one is the third root of x to the 15th. The easiest way to think of that is probably to change this to a rational exponent, meaning a fraction. So remember that your root is the denominator. The power that you're raising it to is the numerator. 15 over 3 is 5, and so it's just x to the 5th. All right, here we are going to evaluate the exponential that is a fraction. So we're looking at fractional exponents. So I have 121 to the 1/2 power. If that bothers you, go ahead and just change it to a square root. Remember that the denominator tells you the root. Square root of 121 is 11. Here I have 64 over 81 to the 1/2 power. Well, that's the same thing as the square root of 64 over 81, which is the square root of 64 over the square root of 81. Square root of 64 is 8, square root of 81 is 9, and we have 8/9. Here we want the cube root of, and notice the parentheses, negative 27. So we want the third root of negative 27. We can do that because that index is odd, and that would give us negative 3. Here notice that the negative is not in parentheses, so that is not included in what you are taking the root of. So what we want is the negative of, and you've got to be really careful here with how you write this. We want the negative of, then we want the fifth root of 32, and then we are going to raise that to the third power. Well, I'm going to want the negative of whatever I get, so I'm just going to go over here and put a negative, because I know this is going to just get drug along. So the fifth root of 32 is 2, and 2 to the third power is 8, so what we want is 8, but we want a negative in front of it, so negative 8. Not difficult, but you have to be careful of those details. Here I have 81 to the negative 3/2. Deal with the negative exponent first. We know that that means 1 over 81 to the positive 3/2, which is 1 over the square root of 81 raised to the third power, or 1 over 9 cubed, which is 1 over 729. So you've got to be real careful. I put a lot of different negatives. A negative inside the parentheses goes inside the radical. A negative outside gets drug along. A negative in the exponent land means the reciprocal, or 1 over. All right, looking at our next page, it says to write these expressions using radicals. So we're just changing exponential notation to radical notation. So the first one is 8 to the 3/4. What that means is the 4th root of 8. Now, raised to the 3rd power can either go inside the radical sign or on the outside after you take the 4th root. It doesn't make a bit of difference. I prefer to do it this way. Here I have 3p raised to the 3/4 plus 4x raised to the 1/3. Not a lot you can do with this. All we can really do is to say that we are taking the 4th root of 3p. Now here, with that raised to the 3rd power, you do not want to put that inside because it's going to look like only the p is raised to the 3rd. So that needs to go on the outside, plus the 3rd root of 4x. And that's all you can do with that one. It's kind of an ugly answer. Here I have a negative exponent and it belongs to everything in parentheses, so I know it's 1 over. Let's keep that 2m in parentheses, and now it's going to be raised to the positive 3/2. To write it with a radical is going to be 1 over the square root of 2m, and again that 3 being raised to the 3rd power, you don't want to put it beside the m because it's only going to apply to the m. It actually applies to the whole thing. So it's 1 over the square root of 2m, and then all of that is raised to the 3rd power. So you have to be very careful with the details of these. Starting with number 17, it says simplify by first converting to rational exponents. So what we have here is 5. Now remember, the index here is implied. That goes on bottom, and then 10 goes up here, but 10 over 2 simplifies to just 5 to the 5th power. And I certainly don't want you to multiply that all out. Here I have r. Again, implied 2 goes on the bottom. Simplify that fraction, and it's r to the 25th power. It's all there is to those. Here we're going to simplify each expression, making sure to write all of our answers with positive exponents only. So what I have here is an example of the product rule. I am multiplying like bases, so what I do is I add their exponents plus a negative 1/3. Now, in order to do that, I have fractions with unlike denominators. So I have to find a common denominator, and I'm going to do this sort of on the side. 2/5 and 1/3, I need a common denominator, which is 15. This would be times 3 times 5. So what I really have is I have x raised to the 6/15 minus 5/15 is 1/15. So not only do you have to deal with the rules of exponents, when you multiply like bases you add the exponents, you have to deal here with the rules of fractions. All right, this one, I see that one of the first things I have is a negative exponent. So to make that happy, I'm going to move that up here. That's going to give me z to the 3/4 times z squared over z to the 5/4. Now there's a lot of different ways you can approach this. I could combine the z's in the top by adding their exponents, and in fact I think that's what I'll do. But the other option is you could have simplified this first and then moved that z squared up. There's just a lot of ways to approach it. So let's think of this as 3/4, let me scoot this over so you can see it, plus 2 over 1. I need a common denominator, which is 4. So 3/4 plus, multiply by 4, 8/4. fourths, so I've got z to the 11 fourths over z to the 5 fourths. Now you have to know the quotient rule, which says if you were dividing like bases, you subtract. So 11 take away, they already have like denominators, by the way. 11 take away 5 gives us z to the 6 fourths, and now I need to simplify that, which is z to the 3 halves. So there is a lot going on in these. You want to be very, very careful. Let's look at this one. There's so many different ways you could approach this one, but because the numerator has its own outside exponent and the denominator has its own outside exponent, I'm going to apply those outside exponents separately. I'm not going to deal with the negative part. I think that's going to confuse you. So when you have an inside exponent times an outside exponent, that's what you do, is you multiply. So it's a to the, it's 2 times 1/4, all right, 2 over 1 times 1/4, which is 2 fourths or 1/2, and it's a negative. And then I have b to the 5 over 1 times 1/4 is negative 5/4, so that's how we begin. Over, now let's do the same thing in the denominator. Negative 3 over 1 times 1/6 is negative 3/6, which is also negative 1/2. And then b to the 2 over 1 times 1/6, that's b to the 2/6, or you can simplify that to b to the 1/3. So you've got to know about fractions and the exponent rules. Here now, I'm ready to simplify further, but I see that I have a to the negative 1/2 over a to the negative 1/2. That's something over itself, and it just cross cancels, making a 1. This is a negative exponent, so it has to change locations, leaving nothing but a 1 on the top. And then I have b to the 5/4, b to the 1/3 in the denominator. Now I'm using the product rule, where I combine in multiplication like bases by adding their exponent. So I need to add 5/4 plus 1/3, meaning I need, of course, a common denominator, which in this case is 12. So this is times 3, and this is times 4. So what I end up with is 1 over, don't forget the 1 over part, and then I have b, then I have 15 twelfths plus 4 twelfths is 19 twelfths. Not a very pretty answer on that one, and there were a lot of things that you had to remember. Okay, let's look at the next page. Here it says multiply if possible using the product rule. So it's wanting us to use the product rule. The product rule states that if you have the same index, you can multiply the two radicands. So this is just going to be the square root of 14 times x. That's an easy one. This one, my indices are both 3, so I can just say 3 times 6, and I get cube root of 18. Again, an easy one. Here, I could work this in multiplication if I change these to fractional exponents, but that's not what the directions say. It says using the product rule. Well, because this index is 5 and this is 6, it can't be done. It can't be done using the product rule. And I'm going to write that because it can be done using, well, a different way. It can't be done using product rule. All right, here it's asking us to express each radical in simplest form again. So this is where we have to break down. Square root of 121 is 11, so that is gone now. The square root, let's do this separately. The 11's on the outside. Of x to the 6th would mean x to the 6th over 2. So all you're really doing is taking this and dividing it by that in your fraction, and that is x cubed. So we end up with 11x cubed. I want you to pay special attention to this one, because this is one where you have to break down what's under the radicand so that you have perfect square factors under there. So 300, and I'm taking the square root, we're going to break down into 100 times 3 because 100 is a perfect square. Z cubed, we're going to break down into z squared, z to the first. Notice that still makes z cubed, but this one is a perfect square. So now I'm going to pull out my perfect squares. Square root of 100 is 10. Square root of z squared is z. And then I can't take the square root of 3 or z to the first. So those remain under the radical sign. So you're only breaking out the ones that are perfect squares. All right, number 28, we want to use the Pythagorean theorem to find the unknown length. We know that that is a squared plus b squared equals c squared. We know that the c has to be the one across from the right angle, and the other two, it doesn't matter which one is which, so I'm going to call that one a and that one b. So that gives me 6 squared plus, I don't know, b squared equals 9 squared, or 36 plus b squared equals 81. Subtract the 36 from both sides and you get b squared equals, b squared, sorry, equals 45. Now to find b, we take the square root of both sides. The square root of b squared is b. And I have square root of 45, but I need to break that into its perfect square factor of 9 times 5. So I end up with b equals 3 square roots of 5. So don't stop at b squared equals 45. You want to continue that until you have solved for b. All right, example 29 is another important one. It's very similar to 27 in that we're going to have to break these down into perfect square factors before we can add or subtract them, because we can only add and subtract like indices with like radicands. So I've got 9. I'm going to break 27 into 9 times 3. P squared is good because I can divide it by 2, so that doesn't need to be broken down. Minus 14. Now I'm going to give you a little tip here. If you don't know what the perfect square factor of 108 is, use this one as a clue. I know here that the 9 can be broken out with a 3 left. So what I want to have left here is also a 3. And when you divide 3 into that, you get your perfect square factor. So it's kind of like I cheated, sort of, kind of, not really. Okay, next one, we're going to do the same thing. I know that 4 goes into here, but that would leave a 12. And I wanted 3 to be left so that I can combine these. So I find that it's 16 times 3. Now we're ready to break everything out. So I already did it here. Square root of 9 is 3. That comes out front. Square root of p squared is p. That comes out front. So what I have here is 27p radical 3. Square root of 36 is 6. Square root of p squared is p. So what I have here is 84p radical 3. See what I meant about how they match? That's what I was talking about. Here, square root of 16 is 4, square root of p squared is p, and I have 8p radical 3. Now, can we combine those? Yes, because the indices are all square roots, the radicands are all 3, and the coefficients are like terms. 27p minus 84p plus 8p is negative 49p radical 3. So again, a lot going on in just one problem with your radicals. All right, let's go to the next page. I hope I'm not causing you seasickness when I move this up and down. On the next one, we are simplifying here also. And what I'm doing is I'm adding fractions that have unlike denominators. So just like any other fractions whose denominators were 3 and 6, we need a common denominator. In this case, that common denominator is 6. So my second one is already good. Here you say, what do you do to 3 to get 6? Times 2. So you multiply the coefficient times 2, not the radical 5. So I've got 4 radical 5s plus 1 radical 5 is 5 radical 5s all over 6. All right, let's look at some multiplying and dividing of radicals. Here we have what looks like FOIL, and it is, so we're going to go first. Radical 3 times radical 3 is just 3. Think about it, because it would be radical 9, which is 3. So when you multiply a radical times itself, you just get what's underneath. Radical 3 times negative 2 minus 2 radical 3's. 1 times radical 3 plus 1 radical 3. And finally, last, 1 times negative 2 is negative 2. Now we need to combine like terms. So 3 minus 2 is 1. Negative 2, positive 1 is minus 1, radical 3. And it's not necessary to show that second one. It could just be this, whichever you prefer. Very necessary to show the first one. Another FOIL. This one is difficult because there's coefficients. You've got to be really, really, really careful. So here we go. First times first. 3 times 2 is 6. Radical 2 times radical 2 is 2. So I'm going to have to do that multiplication there. So that's the part that's difficult. Here we have minus 9 radical 2 plus 2 radical 2 and then minus 3. Well, this first gave me a 12, and then I have that minus 3. And then negative 9 radical 2 plus 2 radical 2 is minus 7 radical 2. 12 minus 3 is 9 minus 7 radical 2. Please remember, you can't combine those and make that 2 radical 2. Those are not like terms. It's sort of like 9 minus 7x. You can't combine those. They're not alike. Number 33. My caution here on this one is just to remember to write it twice. So it's square root of 13 minus square root of 2 times square root of 13 minus square root of 2. Don't just square the two pieces. You have to FOIL this. This makes 13 minus square root of 26. Those are both radicals, so you can multiply them together. Minus square root of 26. Negative times negative is a positive. Radical 2 times radical 2 is 2. Combining like terms gives me 15 minus 2 square roots of 26, because each of those is a 1. Here it's telling us to rationalize the denominator, which means to get rid of what radical is in the denominator. Here I do that by multiplying by radical 2 over radical 2. That gives me negative 6 radical 6, multiply your radicals, over 2, and that can be simplified. 2 goes into 2 once, it goes into 6 3 times, so I have negative 3 radical 6 all over 1. Now remember, you can't cross cancel outside the radical sign into inside the radical sign, so I can't cross cancel those two. Here, I can't just multiply by the radical. I have to multiply by the conjugate, which is square root of 6 plus 3. Square root of 6 plus 3. We're going to distribute here, so that's going to be negative 5 radical 6 minus 15 over. Here we are going to FOIL, so that's going to give us 6 plus 3 radical 6 minus 3 radical 6, those make a 0, minus 9, which is a negative 3. Now that answer is technically correct, but I don't like to leave division by a negative. So division by a negative causes all the signs to change. So what we have is 5 radical 6 plus 15 over positive 3. What you cannot do here is cross cancel that 3 and the 15. And the reason is this numerator is a unit, and you would have to cross cancel it both directions in order to do that. And you can't, so just leave it as it is. The last one, it says to write in lowest terms. This sort of goes back to what we just did with number 35, in that you can't cross cancel part of a numerator. I can't cross cancel this 6 into this 18 because there's another part of the numerator. So what we're going to do is break down the radical. So negative 18 27 is going to be 9 times 3 over 6. Square root of 9 is 3. So that's negative 18 plus 3 radical 3 over 6. Now what I want to show you here is that I can cross cancel now if I can take something out of all three parts. So I have this part, this term, this piece, and this piece. And what goes into all three is 3. So 3 goes into 6 twice, goes into that once, it goes into this 6 times, and we end up with negative 6 plus 1 radical 3 over 2. And no, you cannot cross cancel that 2 and that 6, and the reason is because of that 3. There's a third part there, and it doesn't cross cancel. All right, looking at our last page, number 37, we're going to solve some radical equations. The rule for solving radical equations is to isolate the radical and then square to undo the square root. So to isolate this radical, I have to add a 3 to both sides, so that gives me square root of 2x minus 3 equals 3. And now I can solve that by squaring both sides, because squaring is going to undo the taking of the square root and get rid of that radical. So what I'm left with on this side is 2x minus 3. 3 squared is 9. Now I just have a linear equation, so I add a 3 to both sides. 2x equals 12, divide by 2, and I get x equals 6. Notice I didn't write it on the blank yet, on the answer blank. And the reason is, when you square to solve something, you are required to check your answer in the original problem to make sure that it works. So we're going to take the 6, put it into our original problem before we even moved that 3. So it's got to look exactly like the original. So that would be square root of 12 minus 3 equals 0. Square root of 9 minus 3 equals 0. 3 minus 3 equals 0. It checks. Now we can say, yes, our answer worked. All right, let's look at our last one. What's under the radical is already isolated, so I'm going to go ahead and square that and square this side, and this is the danger, is on the right. The left-hand side is just x squared plus 3x plus 7, but to square this, you have to write it twice and FOIL it out. Don't just write x squared plus 4, that's not right. When you FOIL that, you're going to get x squared plus 2x plus 2x plus 4. So see, I didn't just get x squared plus 4. I see that I have squared terms, so I want to get everything on one side equal to 0. So I'm going to, they happen to go away on both sides, so I have 3x plus 7 equals 4x plus 4. I'm going to subtract the 3x to get variables all on one side. X plus 4. And I end up with x equals 3. But again, because you squared, you must check your answer in the original equation. So 3 squared plus 3 times 3 plus 7. Does that equal 3 plus 2? Square root of 9 plus 7, is that 5? Square root of 25, is that 5? Yes. So it just so happens that in both of these problems, our answers checked, but there are times when they don't, especially if you get two answers. Sometimes one of them doesn't work.